Okay, AP Physics C, static forces review really quick. All right. The whole thing with static forces is net force in the x direction has to be zero, net force in the y direction is zero. So we get all these various setups with ropes and gravity and a normal force and some other angled force over here, all acting on some object, right? F1, F2, F3, and F4, we'll call them. Well, what we do is we put them on a coordinate system. And we always make that coordinate system so that as many forces as possible are located on axis, meaning on one of the coordinate axes. Coordinate systems are changeable. They can be oriented any way you want them to be oriented to make the math easy, right? So then we'd have a few different angles here. We'll call this theta 2, theta 4, something like that. So the way we attack these problems is we draw a force diagram, and then we try to figure out how they balance, right? So we do Fx, right? You'd say F net x must be equal to 0, and we'd add up all the x forces. So F2's x component plus F4's x component must add up to equal 0. So their two x components, in fact, must be equal to each other, right? F net y must also be equal to 0, right? Because it's static. Everything's held in place. So F net y is 0. So that means that F1 plus F2y plus F3 plus F4y must equal 0. So in this case, F1, F2y, F4y, those components are all positive, and they must equal F3. Now, sometimes what people do is they put all the positive components on one side, negative components on the other. I prefer to write out the sum of the forces equals 0. Sum of the forces equals 0, because that harkens to Newton's second law, F net equals ma, or the sum of the forces equals the mass times acceleration. Well, ma in this, like we learned in the lab, right? Ma in this case is 0 because the acceleration is 0 because it's a constant velocity. All right. Now, how do we find these components? X components, Y components. Now, we've already done multidimensional motion, so you should be remember how to find components, but you just take the angled vectors. You'd have to be given these angles, or you could be given the magnitudes of the forces and find the angles. You could be given this a number of ways, but any way you get it, you'd have to say, okay, F for x equals F4 times the cos of theta 4, F for y equals F4 times the sine of theta 4, theta 4. Oh man, I'm out of the frame, my bad. Over here I would say F2x equals F2 times the cos of theta, F2y equals F2 times the sine of theta, right? And then we take those and plug them in over here and do big algebra problems, right? So ultimately, all static force problems end up, in some sort of situation like this. Now, we'll do many specific examples here. The one that we always kind of start off with, though, is the good old force diagram. It's one of the most popular force diagrams in all of physics, where you have, it could be anything, right? It could be a ball hanging from a string, and it's moving at a constant velocity, but there's air drag, holding it back, and it's at some angle like this, right? It's a ball. Maybe it's hanging from your your hand, and you're running, and it's tilting backwards, but you're going at a constant velocity, right? So there's some sort of drag force holding it backwards. there's some sort of tension here, there's some sort of gravity here, right? Let's say the mass of this ball is 0.20 kilograms, right? And let's say you estimate the angle that it's hanging at here, theta, to be, I don't know, 35 degrees, okay? And I say, okay, tell me what the drag force must be. Okay, so determine the drag force on this ball. You're running constant velocity and you're making an angle. You know its mass. These are easy to measure. Tell me the drag force. That's something that would be very hard to measure directly, right? How the heck do you do that? Well, you could do it this way. All right, so we go x direction here. In the x direction, we would have Ft x plus the drag force must equal 0. All right, so that's x direction. In the y direction, and no, I made it the sum of the forces here, right? I just made it the sum of the forces. When I start plugging in variables and numbers, I'll put signs on these. In the y direction, I have Fty plus Fg equals 0. So, Ftx, that would be, well, it's going to be actually sine, right? Because we got to get that component of the force, right? And this is the angle. We need this component, Ftx. Fty is going up here, Fty, opposite. So Ftx is Ft times the sine of 35 plus F drag. I'm going to leave it positive here and see if the numbers end up working out. All right, we'll see what happens here. In the y direction, we have Ft times it's actually going to be cos of 35 here, and mg is going to be 2 newtons, but I have to make it negative because it's pointing down. All right, so now we have two equations. We have two unknowns. We have Ft and F drag. So this one we can solve for the force of tension, the magnitude of the force of tension we can get from this one. And it's going to be, bring the negative 2 over to the right, so it's going to be 2 newtons divided by the cos of 35. All right. So 2 divided by cos of 35 is about 2.4. So the force of tension has a magnitude of 2.4 newtons. So over here, this component for the tension is positive, right? So it's going to be 2.4 newtons times the sine of 35, and it's going to be positive because it's pulling to the right. And then when I bring the F drag over here, right, it's going to become, well, actually, I'm solving for F drag, so I'll leave that on the left, right? So 2.4 times the sine of 35, so F drag equals, I bring this over here, this ends up being 1.4 newtons. I bring it over here, I get F drag equals negative 1.4 newtons. Boom, done. That's the drag force. So this is the basic procedure for a basic problem. This could be a drag force. Maybe this is a electrostatically charged tinfoil ball and it's being pushed by an electric field. Maybe there's no force and it's something being accelerated to the right and you want to figure out the acceleration. Maybe there is no force going that way, but there's a net force pulling to the right from the tension accelerating it. Maybe it's like number 1, an 80-kilogram canoe suspended from a tall garage's ceiling by a chain. Who knows? But this is the general procedure for solving static force problems. I draw the force diagram. Any angled forces I break into x and y components. I set up Newton's second law in the x direction and the y direction. I like to do sum of the forces equals 0. Now, I could have done this, force of tension minus the force of drag, right? I could have done that. Some people like to prefer to do that, and force of tension minus the force of gravity equals 0, because, you know, that's going to the left. This is going down, right? And when you do that, you end up you bring this over here, and you basically end up solving for the magnitude of the drag force, which I don't particularly love. I want to get the sign right, So I like to keep it the sum of the force. Over here, you end up getting, you know, you bring this over here, Fg equals, you know, you end up getting positive, negative 2 newtons, you know, I'm sorry, this would end up being, you know, well, I guess you'd probably go the same way here. You just got to be careful not to put in 2 negative signs and end up making this positive, you know. You already counted for the negative g when you made this sign negative. So don't, you got to avoid sign errors, you know. So I prefer to do sum of the forces, and then the signs will work out the right way in the end. All right. So that's the basic review. The other thing you want to watch out for is friction, right? Friction and tension are the two main forces here. So just a quick review on what frictional force is. So frictional force is the force of a surface acting on another surface. All right. So when an object sits on a surface, there are, believe it or not, chemical bonds that set up between the two objects, right? So when you pull it, right, there ends up being friction at this surface, right? This block wants to stick to this surface, and you're pulling it, you're sliding it, you got to break those bonds it had when it was sitting there, and then you need to keep it moving. Now, not only is it chemical bonds, but if I actually zoomed in here on like a more microscopic level, right, we'd see two surfaces that no surface perfectly smooth. We'd see two surfaces kind of rubbing against each other, catching on each other, and so on. Actually, very smooth surfaces can be very high friction if they're like, for instance, two pieces of glass. My battery's running out here. Two pieces of glass stuck together, and you try sliding one of the pieces of glass, like in chemistry or bio or anatomy, when you make like a microscope slide, those pieces of glass stick together like crazy, right? So smoothness isn't always a good indicator. Anyhow, the force of friction acting on something is equal to, like we say, the coefficient of friction times the normal force. Coefficient of friction, right? Mu. I gotta wrap this up here so this video doesn't cut out. All right. This is a percentage, right? It's a percentage of the normal force. It ranges from like 0.2 up to about 0.8. And it's a percentage of the normal force. And you're typically given these. You have the kinetic coefficient, which is while it's sliding, and you have the static coefficient, which is while it is at rest. And we will also have a rolling coefficient if something is rolling. All right, normal force is the contact force between the object and the surface. Usually this is just equal to mg, right? But if you have multiple things stacked up or an extra force pushing down, then that normal force is going to have to factor that in. All right, so the heavier something is, the more force of contact there is with this between the two surfaces, the more friction there is. All right, so that's that one. Tension, rope, pretty straightforward, right? We dealt with that in the lab already. It's always pulls on both objects with the same amount of force, Newton's third law. All right, so just to get you started on that worksheet, Unit 3, Worksheet 1, really want you guys to kind of try to dig deep on that one and see if you can remember that stuff, okay? Some of these basic problems. Okay, have a good one.